right.
So she's saying
Right after I remember, they remind me. Okay. So what we were talking about was this first problem was arithmetic sequences, and it's because there's a common difference. And we were talking about the recursive formula. So the recursive formula, you have to state what the first term is, and then you have to state what you need to do to get to any other term. Now, this little pattern here, this one right here, it was helping you develop the explicit formula. So you should have noticed that each time the number of common differences that you added was one less than the number of terms. So when you got to this last one, the nth term, you would have stated that to find the nth term, you take the first term plus n minus 1 d's. So d times n minus 1. And so that's how we built the recursive and explicit formula. Now this would have been a lot of stuff if you hadn't been introduced to it last year. So it was just kind of triggering, hopefully, some memories.
That's
Now,
just for arithmetic, correct?
this is just arithmetic. The second sheet was geometric. So when we graph it, this graph is totally right. We just have a bunch of dots. They're not connected because it's discrete information. And when we look at sequences, when we talk about the number of the term, if I line the class up, I'd have the first person, the second person, the third person, the fourth person. That's kind of like a sequence. There's not a 3.5 person, is there? So when we look at the domain of a sequence, when we're graphing a sequence, our domain is the set of counting numbers. Does anybody know what those are called? The counting numbers is the set of
integers.
Close. It would be you could say positive integers.
Real numbers.
Real numbers gives us the decimals and fractions too. So
Whole numbers.
natural numbers.
Natural.
That was my 7th.
Actually, whole numbers is correct.
Nice.
Because it's not zero.
Yeah.
Oh, whole numbers had zero. Natural numbers is correct. Natural numbers is a set of counting numbers. Okay, so when we graph it, when we graph sequences, we would not connect the dots. Now, in context of the problem, we can determine whether or not drawing in a continuous graph is appropriate or not. But generally, if we're modeling something as a sequence, then that domain is a set of natural numbers, and it wouldn't be continuous. Okay, so in this section, you are just supposed to decide, given this formula, we know the first term is this. Well, the first term is the same as our, when we plug in, we can figure out our y-intercept, and this is our slope. So they were just relating the two things. How does slope and y-intercept relate to the two forms? So we would plug in 0 to find our y-intercept. We can find our slope because our slope is the same as the common difference. Okay?
Yes, ma'am.
Now, this one kind of threw a wrench at us, didn't it?
Yeah.
Because this is not arithmetic. The first difference is not constant. But did you notice that the second difference was? And what does that key you into? If the second difference, very good. It is quadratic.
Yeah.
So now we know it's quadratic. Let's see if we can just look at this and figure out what to do. Well, this second one makes so much more sense to me. To square the number of the term and add 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5. 3 squared plus 1 is 10. 4 squared is 16 plus 1 is 17. So what would this term have to be? 11, because 11 squared is 121, plus 1 is 122. Or once we come up with this pattern, then we could just set it equal to 122 and solve. So you may have been able to do it this way. You may have had to plug in.
Is it always going to be that pattern, or does it change?
No, the patterns change. But they just gave us a sequence of numbers, and can you describe that sequence given a formula?
True.
So, given that the second difference was constant, that was our key there, that it was quadratic. Remember when we studied the quadratic unit last semester? We would subtract the differences twice? Yeah. Okay. All right, so now let's take a look at geometric. With geometric, we had a common ratio. That ends up being a number that we multiply by over and over and over again. Okay? And when we model a geometric, it ends up being an exponential, doesn't it? When we multiply by that common ratio over and over and over again, times r, times r, times r, times r, we can write repeated multiplication as an exponent, can't we?
Yes.
So it becomes the first term times r to the n minus 1. And so this was trying to talk us back through what we learned last year when we developed this formula. On this one, because we're modeling a sequence, it should be discrete, but in order to see the exponential function, we drew in the line. But it should be discrete once again. And then how do you find your rate and your first term? Well, you would plug in 1 to get your first term. Do you see how both of these equations are not quite in the right form?
Yes.
They're just raised to the n instead of to the n minus 1. If they were to the n minus 1, then the first, this number right here, would be your first term, wouldn't it?
Oh, but it's not because you
But
have to
it's-
multiply them together.
Yes. But it's not because it's raised to the n. So we had to plug in 1. So that was a little, and both of them were the same way. Probably should have made one of them n minus 1 and the other one a trick to it, but both of them had the trick to it. Now, if these were in terms of a word problem, we would say this is growth because as if this one is increasing, this one is decreasing. If they were in terms of a word problem, we could label them exponential growth and exponential decay. Now, this one right here is pretty cool because it's switching signs. When it's switching signs, we know that r is
Negative number.
negative. Yeah, because the negative number to an even power is positive and a negative number to an odd power is negative, and that keeps it changing signs. Okay, any questions on everything you can see? I know this is not all of it because I kind of shoved it closer together to get it on 2 pages instead of 3. Yes, ma'am.
Okay, so like I understand that a lot of this is like n minus 1, like the number, you like the previous number plus or times the value. But like I don't understand how you find the previous number.
Okay, you only need the previous one if it's the recursive formula, this one. Otherwise, you don't have to have the previous term. You just need the first term. The first term times the rate to the n, times the common ratio to the n minus 1. Okay? All right, and so here they've given us a formula. They ask us to find the first 5 terms. Well, we can just continue to multiply by a fourth. And to find the 10th term, you would plug in 10, so you get 2 times 1/4 raised to the 10 minus 1, which is 9. And that gives us 1 over 131,072.
So when it's raised to a number minus 1, you know that the first number is already there. Already there.
Correct.
Okay.
When it's raised to the n minus 1, we know that this is the first term.
This is 2 right there.
Because if we plugged in 1, this becomes 0, and anything to the
that's
0
true.
power is 1. Yes, Sid.
Do you want to do like decimals with that, or like
Was it a pretty terminating decimal?
Number 7
Yes.
was. Number 10
Well, it wasn't
Was
pretty.
it nice and short, a nice little pretty terminating decimal?
Yes.
No, it was a long,
They were,
ugly, you couldn't see it all decimal.
What they said.
You
So,
tried.
so I wrote it as a fraction.
It was 7.6 e negative 6.
All right.
So anyway, they've been standing up for a while.
Okay. Y'all get ready because I'm about to give you 1 minute to do something.
Oh, God.
But you may not use a calculator. All you need is a pencil.
Why is so cute?
Okay?
So it is not.
And
There's a pop quiz?
No way.
Yeah, pop one.
you only have 1 minute to do it.
Oh god.
I felt like I've been too easy on you guys and I needed to up the ante.
Listen, Jones. I told you. I said this in second period. I'm gonna come in and masturbate. I'm gonna have a pop quiz. I'm gonna cry.
Oh, good. That'll make it more fun. All right, everybody ready?
One, two.
Wait, 1 minute.
Wait.
1 minute. Go.
No.
Can you find the sum of the numbers 1 to 1,000? And you now have 57 seconds left.
I give up.
Oh, dude,
When you
we're
find
gonna
the
do
sum of the
that.
numbers 1, 2.
I feel like this is a trick question.
Yeah, it's gonna be a
Okay,
trick
you gotta
question.
add faster than that. Come on.
The real answer is actually.
Whoa, this is just a yes or no question.
Oh, you gotta do that.
Can't use a calculator.
Yes.
It is a yes or no question.
No, I know how to do that.
I wrote.
No.
1, 2, 3,
Oh, gotcha.
Yes.
And
So we have to write it down?
I can do it, but I don't know.
And if you gave me my phone number, I could.
Some
The trick question, see, all those letters cancel out on each other.
Oh, you just put 1,000 over the whatever thing, right?
So true.
I was watching the comprehension video on this and I was so confused.
Maybe now you'll understand.
Okay, 3 seconds.
I'm done.
Anybody got it?
Yes.
It's a
Yes.
Brian is actually like,
He
doesn't
everything.
I don't know if this is right. It may be close though. 55,000.
You have the right idea.
Yeah.
You do have the right idea.
Yeah, I think we're just wrong.
Yeah.
No.
I don't.
Brian's answer is
No.
no. And I do kind of like that because it just says can you. It doesn't say fine. All right. So
I'll give you credit for that one.
that is an honest answer.
Yeah.
I love it.
I like the direction Brian's heading in, and the same type question was posed to this little fella who's now deceased. But when he was in elementary school,
Gusses.
Goss.
Goss.
Goss. So, Carl Frederick Goss.
There's a space.
Okay, so, you know how all parents hope their children are really bright?
Yes.
Well, this little fella's parents got more than they bargained for.
This was like a genius.
He was like a genius.
Was he?
So,
It's like when
So he was around from 1777 to 1855, and obviously he didn't have calculators to work with. But he was one of those really bright boys in elementary school that was highly annoying to the teachers. Because as soon as he was given work, boom, it was done, and then he was mischievous.
like Joshua Tyson.
So,
No.
but Joshua
Except-
wasn't mischievous.
Oh, he just knows everything.
Yes. Okay. So he was just always kind of anyway. So the teacher said, "All right, go to your desk and find the sum of all the digits of 1 to 100." And he went to his desk and he wrote the answer and he went back.
Miss Wilby?
Tell me how we did it.
Okay.
Don't tell me
So what did this little guy
You
do?
said that.
What he did was, instead of immediately sitting down like some of us would do and writing 1 plus 2 plus 3, he was like, okay, there has to be a better way to do this. And he quickly figured one out. He said, all right, this would be painful.
Well, maybe one time
And
he
take
got
a
really
while.
bored and did that, and then he just went to his desk and remembered the answer.
But
So if you add up 100.
if I took it and went up one direction and down the other,
It's all equal. 101.
every time I get the exact same sum, don't I?
Yes.
I get 101. I get
We
101.
multiply that by.
I get 101. I get 101. All and my final term is 101. But I have a problem here.
Why?
I only wanted 1 to 100. I didn't want 1 to 100 and 100 to 1. I doubled my work, didn't I?
Yes.
So you
So
gotta
instead of taking this and multiplying by 100, I'll take this and multiply by 50.
Half of the original.
Half of it. So instead of doing 101 times the 100, because that's how many of them that there were, he divided that by 2. So he did 101 times 50. So he wrote down a 0, and then 5 times 1 is 5. 5 times 0 is 0, and 5 is 5. And that's what he wrote on his blackboard and that was it.
Wow.
It was an elementary
You were
school.
close to
What grade?
So that is the story. Now, I've read it cited in many different places, but in some of them, it says this was the story that was told to the biographer. It
Whether
may
or
or
not
may
it's
not have been
fabricated or not.
validated by other people.
True.
So, it is very interesting. It also says that when he was 3, he corrected his father's financial papers. Yeah. So,
That's true.
Gauss is a very famous mathematician. And if you read about him, he's also was somewhat of a perfectionist, which a lot of people that think in that direction are somewhat perfectionists. And he is credited for many things in mathematics, but there are many more things that he worked on, but he never published because he never felt they were perfected. And then other people picked up his work and finished it, and they received the credit for it.
So they were cheaters on the test?
Anyway,
This is the
Final
guy
exam,
that
they cheated?
as an elementary student, he discovered what we're going to work with today. How to find the sum
I feel so smart.
of a sequence of numbers.
So this
That
guy
is-
came up with it when he was
That's
younger
not
than
that
us?
hard, you just
That makes
add
me feel
yes.
whatever the original
No,
number
no.
is
I can't
plus
even-
No,
one
he was brilliant.
times
You're not.
50.
So what we're going to do is we're going to do a series, and that is basically when we take a summation, and that's the symbol in mathematics for summation is the Greek capital
Sigma.
letter sigma. That is correct. But in mathematics, that stands for summation. So we're going to find the sum of the terms in a series. Any questions? Okay. Now we are about to somewhat develop a proof for what Gauss did. Okay, and let's start out with the same idea. But let's show that it doesn't just work on 1 to 100. That it doesn't just work with a common difference of 1. That it would work for any arithmetic sequence. So if we're working with any arithmetic sequence, we better be dealing with this formula. Isn't that what we used yesterday? And we developed this formula yesterday. Okay? So we're going to be dealing with this, and I'm going to do the same idea. I'm going to say, okay, I want to find the sum of terms. So I'm going to say, okay, the first term is a sub 1. Let's switch colors up on it. Okay? And then I'm going to add to that the second term. And to get the second term, don't I just add a common difference? A sub 1 plus a common difference. That gives me the second term. You got to pay attention. You can't zone out. Okay, good. Okay? Now, to get the third term, wouldn't we just take that first term and add 2 common differences to it?
Yes.
Okay?
Interesting.
And to get to the next term, we would take the first term and add how many common differences?
3.
3. And then we continue this, wouldn't we?
Yeah.
Until we said, all right, the nth term, the last term. Well, isn't the nth term just this? The last term?
Yes.
It's the first term. Whoops, I need a plus.
So it's a sub 1 plus a sub 1.
How's the last one?
So that's
It's a sub 1 plus n minus 1 times t. Right?
Yes.
Okay. That gives us the nth term, because that's what a sub n is. All right, maybe it would help if I go, okay, this is the first term. This is the second term. This is the third term. This is the fourth term. Got
This is the
extra
nth
humps in
term.
these. And this is the nth term. The final term for us, n. Okay, let's stick with Gauss's idea, and let's go backwards here. So we're going to start with the nth term. Okay, so if this is n minus 1, then the one before it would be n minus 2, okay? And then the one before that would be n minus 3, good. One before that would be n minus 4. Good. And then all the way back to the first term. What would the first term be?
A1.
A1.
Yeah.
Okay, so we're going to take this and we're going to do the same exact thing. We're going to add them. So here I have a sub 1 plus another a sub 1. How many a sub 1s does that make?
2.
2. So we have 2 a sub 1 plus n minus 1 times d. Okay, now these two get a little tricky. The a sub 1 part, not so bad. A sub 1 plus a sub 1 is 2
a sub 1.
a sub 1. But this part right here is a little more difficult. Let me just kind of change colors. I'm going to put it in green up here for a second. So what I'm adding are these two pieces. I'm adding d plus n minus 2 times d. Okay, so could I distribute that d? Would that make d times n minus 2d? Okay, can I combine these two?
Yes.
So that makes d n minus d.
Mm-hmm.
Do we see a common factor of d?
Yeah.
Oh, how cool. Oh, how cool. Look what just happened when I added those two. I got n minus 1 times d.
Well, the same thing.
They're all the same thing.
Just
Over
proving
and
that.
over and over again. Just like when we just use numbers.
Then you just divide that out.
We're getting there. We're getting there. You're right. We are going to have to divide that. So all the way to the nth term, when we add that nth and the first term, we still get the same thing. So we got this. How many times did we get this? N. Didn't we go all the way up to the nth term?
Yes.
We got n times 2a sub 1 plus n minus 1 times d.
Divide by 2.
But we doubled it, didn't we? So we need to divide by 2. That's what we just found.
The equation.
We found an equation. This is one of the equations that will give us the sum of an arithmetic series. You take the number of terms and divide by 2. You multiply that times this. So twice the first term plus the number of the terms minus 1 times the common difference. That is not what Gauss
I
is.
was about to say, that is impressive.
This looks very different,
It
doesn't it?
does.
It does look different. But I'm going to dissect this part
It's more complicated.
into what it was every time. Every time it was a sub 1 plus a sub 1. Not what it was every time? A sub 1 plus a sub 1, a sub 1 plus a sub 1, a sub 1 plus a sub 1. Guys, what is this? A sub 1 plus a
That's
minus
yours.
1. That is the same as a sub n.
All you do is add it.
N divided by 2. The first term plus
And
the last term. Okay. These are basically the two formulas. You
The
don't.
first and the last, or the.
This one.
Is there
And
reason
this one?
explicit?
Oh, okay.
You don't need to know both of them though. You really just need to know this one.
It's almost easiest.
Wait, would that be
Because we already know how to find a sub n if we don't already have it. We know how to find it. So this is really the only one we need. Okay.
that would be explicit, right?
We would have to use the explicit formula to find a term inside of it. That is the formula to find the sum of a sequence. It's called a series.
Thanks, Emma.
When we do the summation of a sequence, we call it a series.
And then,
And so to find the sum is that equation.
all right, Em?
Okay, so the first thing that's missing in your note sheet is the series formula.
Is this our homework?
Fill it in. You know it.
this will be, can
So either
we stick with
the first
the series equals n over 2 times 2a plus n minus 1 times d?
That one's harder
I
sometimes.
like that one.
If they give you the first and last term. So, they both certainly work. And this one actually does, this is contained in here. Because that's how we could break it down.
Sure.
I just don't like to memorize extra stuff.
So if
And
they give us
so-
the first
yeah.
and very last,
If they give you the first term and tell you how many terms there are, then that is a better formula to use, yes.
Don't you have to memorize anyways though? Because if you know what A and N equals.
Okay, so I would say the first of the sum of n terms is n divided by 2, the first plus the last. Because we already know this one, and we just basically could plug that in there if we needed to.
Can I check the golf schedule real quick? Because I think we moved the test back to Thursday. I think we actually have an away match.
We have to do the 12 o'clock for away matches.
What? Yeah, we leave at like 12. So can I just check and see if that
All right. A sequence is just an ordered list of numbers, and we call those numbers terms. We have arithmetic sequences and geometric. Right now we're focused on arithmetic. How do we know when something's arithmetic?
When the common difference is added.
That we have a common difference with arithmetic. Good. So basically that means we're adding the same amount every time. Yes.
Wait, Miss Willoughby? So we change it to the 17th to 18th, or is it the next 2 days?
It's the 17th thing.
Okay, all right.
Okay. Geometric. We don't have a common difference.
Common quotient.
Ratio.
We have a common ratio. And basically, I think somebody was saying that we multiply by the same amount every time. And that's how we know we have geometric. Now we talked about the domain. The domain of a sequence, it's the first term, the second term, the third term. It's the set of natural numbers. And then the range is just that output. It's the terms in the sequence. Now, we just talked about how we find the sum of a sequence, and we've discussed that that is called a series. And we have two types. we have, we can sum finite, and we'll talk about tomorrow, can we sum infinite?
Yes.
So let's talk about the difference. What does finite mean?
It doesn't end.
What does infinite mean?
Does not end.
Does not end.
Yeah.
Okay, and this one's interesting. So we're going to look at this one tomorrow. Can we add it up if it doesn't end? Okay? So there's our teaser for tomorrow. Come back to find that out. All right. So
Or just don't try.
N is going to represent either the position in the sequence or the number of terms in the sequence. And so it just depends on the wording. We're going to look at two arithmetic and geometric sequences. Here are some examples, and let's decide, are they arithmetic, geometric, or neither? The first 5 terms in the sequence can be found using this formula. Would this be arithmetic, geometric, or neither? Arithmetic, because it's linear, right? All right, the first 5 terms in this sequence, is this arithmetic, geometric, or neither? Neither. Arithmetic is linear. Geometric ends up being exponential. So this last one is geometric. So if we actually found the first 5 terms, it would be 7, 10, 13, 16, 19. Okay, and this would be 2, 6, 18, 54, 162. Okay, so you see how you're adding the same amount, here you're multiplying by the same amount. This one would not be like that. It would be negative 2, and then we plug in 2, we get out 1. You plug in 3, you get out 6. You plug in 4, you get out 13. You plug in 5, you get out 22. Yeah, it's not adding the same amount every time, is it? It's not multiplying by the same amount. But if we did the second difference, would it be constant? Yes. Okay, so here are some of the things we could look at and some of the things that we could do. We're actually going to do this first one. We're going to find the sum of this series. We can find terms in a sequence. We can write explicit formulas. So this is old, this is old, this is old. How many terms are in the sequence? We did that last year. If the 6th term is this and the 28th term is that, what is the 19th term? All of these were from last year. Now the sum is new. Okay, so these type questions, when you're finding the sum, that's where we would have to use our summation formulas. Okay? We're going to look at 3 examples today, and then I'm going to let you start your assignment. All right, so here is a series. I know it's a series because we have plus, plus, plus. Looks like a sequence, but we have the plus in between. So on this one, it is clear that I can see the first term. It is clear that I can see the last term, 21. So when we were talking about which one do we want to know, well, this one might be helpful because I can clearly see the first term and clearly see the last. But I am missing some stuff. I need n. How many terms are there? I don't know. But I can tell what the common difference is.
2.
2. It's increasing by 2. Great. All right, so if I just take a look at this part, actually all of this together, aren't all of these part of finding a term?
Yes.
And I have everything but n.
So solve for
So I can solve. So the 21 is the nth term. 1 is the first term. I don't know. But the common difference is 2. Now obviously we're going to solve these as easily as possible. So we'll move the 1 over and get 20. Instead of distributing the 2, we'll just divide by it because we know everything's going to turn out pretty. We add the 1 and we get n as 11. The number of the term has to be a counting number. So when I'm solving for n, I know it's going to divide evenly.
What do you mean number?
So I just figured out that n is the 11th term. So now I can find the sum. So the sum of the first 11 terms is 11 divided by 2. The first term plus the last term. And I've got divide by 2, but obviously I'm going to take half of the 22 because that's easier, right? Half of 22 is 11. 11 times 11 is 121. The sum of the first 11 terms is 121. Make sense?
Yes.
All right. Let's take a look at a different type problem. So this time I don't have the first and the...
So we're gonna use the second, right?
We certainly could. Or we could just find the 8th term.
That's easy.
Okay? So the 8th term is the first term plus 8 minus 1 times the common difference. What's the common difference?
5.
5. So 35 plus 3 is 38. So now we have the last term.
Cool.
So we can find the sum of the first 8 terms is 8 divided by 2. The first term is 3, and the last term is 38. So I get 4 times 41.
Which equals
And so the sum of the first 8 terms is
164.
164. Okay, so let's go back and look at our list real quick. Could you find the sum of the first 20 terms?
Yes.
Sure we could. This isn't a word problem, but it tells us the first row has 50 seats, the second row 54, 58 on the third. We have a total of 30 rows. Could you do that one?
Yes.
Yes. Could you do this one?
Yes.
Yes. Okay, you got 1 minute.
Goodness.
Maybe I should have written 10 on this one.
I already know the end of it.
How many numbers is that? I feel really stupid asking.
If it's all the numbers 1 to 1,000.
Is it 1,000? I'm so sorry. Did I ask that?
You don't need a calculator. Five seconds. Stop. All right, so we said 1,000 over 2. 1 plus 1,000. So it's 1,001 times 500. Well, you don't really do times 500, you do times 5. Because you just start off with the first 2 zeros. And then you do 5 times that. 5 times 0, 5 times 0, 5 times 1.
That's why not.
500,000, 500. Boom! You know how to do it. Okay, I'm going to bow with your homework.
I did